Today I'm going to be taking a look at something that Banggood sent me to take a look at. This is a Nano VNA, which is a vector network analyzer. Its intention is for testing, analyzing antennas and antenna transmission lines and things like that. So in the days before I retired, I used to use test equipment which did some of the functions of this thing, albeit those were multi-tens of thousands of dollars a piece of equipment. This thing is in the $50 to $60 range, definitely approachable by hobbyists. As you can tell by the fact that it's not plugged into anything, it is battery powered. You can actually see the battery sandwiched back in there. There are two RF connectors on it. This CH01 is the one that you're going to be using 99% of the time. And I guess the short answer about what this thing is doing is it will send an RF signal out of a known value, known frequency, known amplitude, and it will analyze the reflected signal coming back. If you're not all that up on RF, if you are sending a signal out to an antenna, transmitting out to an antenna, a perfect antenna, a theoretically perfect antenna, will absorb or radiate 100% of the energy sent at it. In the real world, no antenna is 100% perfect, so there's going to be a certain amount of energy coming back, reflecting off the antenna or splitters or anything else that's out there, an open circuit, for instance, like we've got right now. And that is that reflected power is often measured as standing wave ratio, SWR. And this guy can take a look at that, measure it, analyze it. It can also do some fun things like telling you how far away a problem is in your antenna system. Essentially a bump or an inconsistency in the impedance in the antenna system, which in the real world, in my application, like I said back in my professional career, that would equate to water in a connector, possibly a damaged antenna, possibly a damaged transmission line. And being able to tell how bad it is will let you know whether or not you have to do anything about it. But more importantly, being able to tell how far away it is in physical distances will tell you where to start looking for the problem. And that is the main use 90% of the time that we put our antenna analyzers to when we were working with antenna systems for troubleshooting and whatnot. And if you're into ham radio or any sort of hobby radio, this kind of a tool is very useful for when you're trying to diagnose or calibrate your antenna system. So from default, it's got 4 different displays showing on the screen, all overlaid. It's got the logarithmic reflections being shown for both of the inputs here. It's showing a Smith chart, which is a circular dude in the background that you can just barely see. It's got a phase angle measurement. And it can also show you delays. A Smith chart, it can show you just straight up standing wave ratios. It can show you resistance and reactance. It can show it to you in various different formats. The Q factor of a filter if you're testing it, the conductance or susceptance of a load, series and parallel inductance, phase angle, a bunch of different stuff. Way more than most hobbyists would ever need, and way more than, quite honestly, I ever used in my professional career as well. Anytime you're using any kind of an RF analyzer, the first thing you want to do is calibrate it. And this thing does come with the appropriate calibration pieces as well. It comes with a 50 ohm load, a short, just a dead short, and an open, it is an open circuit, but it's shielded so no stray RF can get into it. So in calibrate mode, you start by connecting the open, secure it down there, tell it what the open is, it checks that off, and then it moves on asking you for the short. tell it that you've given it the short, and then it asks for the load. And you tell it that it's got the load, and then done. And with that, the Smith chart is showing a perfect 50 ohm resistive load right in the middle of the chart, right like it should. So just quick Smith chart for people that didn't take an RF engineering course in college 30 years ago like I did, 40 years ago. This center line is measuring resistive impedance. Anything that is above the horizontal line is inductive reactance. Anything down below is capacitive. So you want your load to be as close as possible to 50 ohms with no capacitive and no inductive reactance in there, which is relatively easy to get to if you've got the right tools and stuff. But watch what happens if I put an imperfect load on there, like just a piece of transmission line of an arbitrary length with nothing particular going on. So now I've kind of made a bit of an error here, because what it is showing is based on different frequency measurement points, and this thing is set right now to be measuring its entire bandwidth between 50 kilohertz and 1.5 gig. So let us change that. Change the start frequency to, let's see, 910 megahertz. And the stop frequency to be 930 megahertz. What that is the North American band where you'd use LoRa. And now I think if we zoom in here a little bit, you can see that my open circuit is quite inductive and kind of all over the place depending on which frequency in that range. But where that marker is 910. And actually, we can move the markers around. Back marker. It's searching for a minimum or for a maximum. Let's search to the right. There's the next maximum. And that is at 915/200. There's what it's measuring for an impedance. So it's measuring 15 ohms, and J86J is the, don't make me go back to textbooks. J is the inductive reactance. In your calculations, it is considered imaginary numbers, but let's not go there. Let us instead add another trace to our display. Let's add trace 0. We'll have trace 0 be standing wave ratio. So now at marker 1, we have standing wave ratio of 13, which is ridiculous. A properly terminated load should show a standing wave ratio of exactly 1. So let's put our properly terminated load onto this, what is this, 20 centimeters worth of cable. Now we can see our SWR line is right flatlined at the bottom, and it is almost exactly a standing wave ratio of 1. Typically, you'll be happy if it's anywhere below, 1.1 or 1.15 area. Most equipment won't complain too much about that, but you obviously want it as low as you can get it. The other thing I was playing with that this thing can do is distance to fault, like I was suggesting earlier. And as I said, that is one of the measurements that I used our antenna sweep gear for at work, the professional stuff, for on a very regular basis. So right now we got about 40 centimeters of line connected, and then in just an open at the end. So that's an obvious fault, so we can see it easily. And for this measurement, I'm in transform mode, showing standing wave ratio. And transform basically, instead of being amplitude versus frequency, it is amplitude versus time. And time, if you know the velocity factor or the specs of the cable, time can be converted into distance. And in this case, we can see the obvious spike of high VSWR, 3.3 in this case, and that works out to 4.39 nanoseconds or 461 millimeters. According to the scale on my desk, my mat is 43 centimeters wide, and this is very, very close to that. So if you're hunting for an error in your transmission line, being 3 centimeters off would make it fairly easy to find. That's less than the width of your hand. Of course, on a longer line, it wouldn't be quite that precise, but still, it's going to get you within a couple of hand widths of where your error is. And if you know anything about how your transmission line is set up or your antenna, you've got a rough idea how tall your tower is, how long your antenna is, where any joiners or connectors are. That'll get you going if you're looking for water in a connector or something like that, which, as I said, is probably one of the most convenient or common faults you're going to find in an antenna system, other than lightning strike or bullets in the line or something like that. And if you're looking for bullet holes in your transmission line, a handy tip is start looking close to where the aircraft warning lights are, because that's where the idiots are going to be shooting at. Did I say that? Anyway, let's go and look a little bit closer at the documentation for this thing. It doesn't come with much. In the box, all it had for documentation is this chart that shows the menu layout, and it is a very detailed menu, very deep menu, so you can get lost. So that is handy to have. But, so the Nano VNA itself is an open source project, which is awesome. The one that I've got, the Banggood sent, is not necessarily one that came directly from the project, but being open source, that doesn't matter because the hardware and the software are both open source. Anybody can do it. But as you can see, the physical characteristics of the one that we've got in front of us are very much the same as the official, in quotation marks, one. If you want to mess with it, all the firmware and code is available. As are useful things from the project, like this block diagram. And if you wanted to dig even further, being an open source project, they even have the full schematic available. Being an open source project, it is fairly well documented on the Nano VNA webpage. So I'm not going to run you through all this. I am going to put a link down below to it as well, though. It shows you how to do calibration. It shows you how to read all the different parts of the screens. It also talks about optional apps and web clients and other software and whatnot, including somewhere in here how to upgrade the firmware. Because it's an open source project, the firmware is being worked on all the time. So if the version that you got is equipped with older firmware, you might want to update that. So way more stuff available in these documents than I have time right now to show you. But I will show you the biggest bonus of this piece of equipment compared to the professional equipment that I used for years at work. And that is that it's available for less than $50 US, or $56 Canadian, or just under 35 euros. And again, I'll put a link to this. Obviously, it's going to be an affiliate link. It's not going to cost you any extra. I'm just going to get a couple of dollars commission if you happen to buy through this link. But there are plenty of places to get these. And as well, as I said, it's an open source project. So if you're really motivated, you can make your own. Regardless, the specs, it is good from 10 kilohertz up to 1.5 gigahertz. It's not putting out a very high RF output, but it doesn't need to. It's fairly safe levels, minus 13 dBm, not a big deal there. Up to 70 dB of dynamic range at the lower frequencies, or even 40 dB at the higher frequencies, which, again, for basic troubleshooting is more than enough. We're not creating lab-grade equipment here. This is a $50 hobbyist piece of equipment, right? Now that I've got this, I am probably going to want to get some additional adapters and jumpers and whatnot. Oh yeah, I forgot about that. You can put an SD card in there and you can save waveforms and stuff to take a look at later. Or one thing that we regularly did when we were installing antenna systems is do a set of measurements on day one, print it out and leave it on the site documents. And then if we needed to check it for troubleshooting later, we had that as reference. And I mean, if you're into ham radio, that would be a reasonable thing to do as well, just to characterize your antenna system and then see if it changes over time, because sometimes they do. I think we saw on the NanoVNA website that there are Android applications available to connect to it. I'm not going to bother doing that because the screen is more than good enough, but you can do a little bit more detailed data analysis on that if you choose to. So one thing I'm going to be using this for in the near future is just checking the antennas on these various LoRa modules, the Meshtastic modules, because I've heard that antennas that come with them may not be the best antennas. So well, let's just try that one and see. It should be 915 megahertz. So looking at it between 900 and 950, that doesn't look happy. This is standing wave ratio versus frequency. So somewhere down in this bottom here is where we'd really want to be. And that is the lowest one. So that's probably what the actual frequency that it's tuned for is. I am going to change the frequencies and see if we can find where our standing waves get the lowest. And again, the marker being at 899 megahertz for the lowest standing wave ratio that we could get. It's still a little bit off of our ideal, but where is 50 ohms? There's 50 ohms right in the center, so it's fairly close resistively. It's a little bit inductive, but not horrible. So I guess that's not the worst in the world. I would still like to see it closer to the ideal center of the frequency band at 915, but so be it. Anyway, that's just a quick introduction to this thing and some of the things that it can do. Other than hobbyists, who else might benefit from this? Well, there's a lot of RF going on in live music these days, wireless microphones and wireless in-ear monitors and stuff like that. So as long as you're under 1.5 gigahertz, which you probably should be, this would allow you to be able to just verify that your antennas, at least your passive antennas, I don't know if it'll work well with the active antennas, but with passive antennas, this would be able to tell you that they're not damaged and that your cabling is, functional and not causing you more problems that it's solving. Might be a good $50 piece to throw in your toolkit for something like that. I don't know. Anyway, thanks for watching. Questions and comments down below. If you got any experience of these things, I'd love to hear about it. Thanks, of course, to Banggood for sending this along for me to play with and to add to my toolkit. I appreciate that. There will be a whole bunch of links down below in the description. I will talk to you later.